Hello, we are from Group 10. We'll present you our own design of Alpha-type Stirling engine. There are some objectives that we have decided based on the project constraints of the course. First, the prototype must be cost-effective. Second, the power output of prototype must be optimized. Third, the prototype must be light. And last one, the prototype must fit within an envelope of 150 times 200 times 200 millimeters. These are the contents that will be present throughout this presentation. Stirling engine is an external combustion engine that converts its thermal energy to mechanical kinetic energy. The configuration of alpha Stirling engine is that the pistons are located in two different cylinders, hot piston and cold piston. The process of this engine is no different than a normal engine, which can be observed as in the slide.
Thank you, Ashraf. So for this part, I will be talking about the process of choosing the design concept of our engine. So, in the early stage of design concept, design sketch number 1 was drawn with the actuator fixed in the V-shaped configuration. However, the problem for this design is that the candle is too far to reach the heating actuator from the base of the design. Next, design sketch 2 was inspired to solve the problem exists in the first sketch. The configuration of the actuator is in parallel and perpendicular to the base. This is to ensure optimum heating process on the actuator. However, both design sketches has the cylinder actuator fixed onto a support, which will cause inefficiency of the heating and cooling processes. Next is the final sketch, which is design sketch number 3, that incorporated the solution to both of the previous sketches. It is in a V-shaped configuration, but the heating actuator is perpendicular to the base to ensure the candle can reach the heating cylinder. Hence, the design sketch number 3 has been selected into a more detailed and critical steps of the design. So, from the help of the technical staff and our mentor, Shin Kinney, the final design assembly of our engine that can be seen in the picture has been made by using SolidWorks. Next is the technical choices and justification that has been made for our final design. Firstly, bracket has been made to hold the actuator at the threaded part. It will be made out of aluminum strips given in the project material, as it only needs to be cut and required less manufacturing steps. It will be fastened onto the stand by using two M4 locking nuts to avoid left and right movement of the bracket. Next is the base of the design. The stand of the engine will be fastened using countersunk screw from the bottom of the PVC base to avoid screw head to protrude out of the base of the engine. Next is the radius of the connecting journal to the center hole of the counterweight. Has been calculated and fixed to ensure the stroke is maximized, which is 1 inch of the actuators. Next, the stand is made from acrylic plate because it will be laser cut into measurement. Next, we use grub screw to hold the ball bearing in place to the stand and the connecting journal to the counterweights. This will secure the ball bearing and connecting journal without the use of any other item such as Loctite and locking nut. Finally, our design used two counterweights to keep the engine in balance. Furthermore, our group has done a FEA bending analysis to further validate the decision made in the technical choices. As we all know, the stand is made of acrylic plate with a yield strength of 17 megapascal. From the FEA analysis that we can see in the picture, the maximum principal stress is roughly 0.05 megapascal, which is much lesser than the yield strength. Same goes to the output shaft, where it is made of steel with a yield strength of 250 megapascal, and the maximum principal stress is only 4.9207 megapascal. This ensures that the part will not undergo any deformation or failure.
For the excellent explanation, I will be presenting my part, which areas that we face throughout the manufacturing process of the engine. The first risks that we encounter are sharp edges from the drilling manufacturing parts from the drilling machine. In the manufacturing process, many of the moving parts should be taken into account, such as drill slip from chuck, metal chips, material slippage. Mitigation plan of controlling most of these hazards are by following the working procedure of the machineries and adjust the manufacturing process accordingly to the need of the end products. There are a lot of controls that need to be considered, and standard safety measures that need to be complied by all personnel inside the working space. Do ensure to wear a safe and proper clothing when working with chemicals such as lubrication and Loctite, or to avoid any entrapments happen with the moving machineries. In case of broken glass or any incident that is like out of the student reach, students shall report to the responsible staff. During the testing session, a critical safety measure should be taken in case of open fire incidents. All attendees should be aware the whereabouts of the fire extinguisher and the evacuation plan. Besides, all electrical equipments need to be checked before the demonstration to avoid any accidental electrocution. This is the overall projected cost from the manufacturing of the engine. However, this cost did not cover any additional costs other than the parts of the engine itself. We spent about $293.21 for this engine. Most of the costs incurred on purchasing of the Apple actuator. The cost, however, can be minimized with some improvements implemented inside the engine parts. I'll pause to make to explain the details on ways to improve the engine while improve the cost efficiency.
Hi, I'm Mick and I will continue the presentation on the improvement section. This section was made without any material or manufacturing method limitation and with the consideration of sustainability aspect. Improvement approaches taken by us is purely on those three aspects: performance, weight, and cost. In terms of improving the engine performance, there are three viable ideas. Firstly, by improving the thermal efficiency. This can be achieved by implementing the fins on the cold cylinder. In theory, larger surface area is better in heat transfer application. Heat dissipates at faster rate and encouraging a larger temperature difference between working cylinders. In addition, applying regenerator on the engine. With larger surface area, heat from the working fluid can either be absorbed and released faster. This helps as it performing preheating and pre-cooling for the working fluid. Secondly, aluminium tube as the alternative for the cylinder material, as aluminium is better at its thermal conductivity and price. In addition, as the tube is cold drawn manufactured, better surface quality is assured by the supplier and friction is considered negligible. For the third idea, stainless steel is much preferred in replacing the aluminium for bracket actuator. This has been proven on the analysis made by our team in terms of vibration. By applying stainless steel, the vibration amplitude can be reduced, and yes, stainless steel is a bit expensive, however this seems to be a good compromise for better performance. This is the result on the vibration analysis. It is clearly can be seen that stainless steel handle vibration much better than aluminum. Next, the improvement also can be made by making the engine weight much lower. It is found that PVC-based steel flywheel and counterweight contribute large portion on the total weight. Based on the data gathered by our team, it is found that reduction of mass up to 60% on the flywheel can be done without compromising its functionality. In addition, this approach also can be reducing the vibration at the output shaft. Next, redesigning the counterweight into crescent shape. By doing this, the mass can be reduced and still able to maintain its moment of inertia. Lastly, large improvement can be made in reducing the mass of PVC base. This can be done by performing topology optimization. However, this process resulting complex shape design and only can be achieved by other manufacturing method. PVC can be dangerous when being exposed to heat due to its high chlorine content. Therefore, PLA seems to be a better material to use as it has good mechanical strength and suitable for 3D printing job. On the downside, PLA can be a bit expensive due to high demand on additive manufacturing application nowadays. To conclude this presentation, our final design on Alpha Stirling engine is considered successful, where all the objectives are being achieved. And now, the engine is ready to be tested. Thank you.